So now I want to give an outline of proof. The principle is we follow Zagier's and Lee's proof. To use their tools, we must do several things. First thing is we must do. First thing is we define a period integral associated to associator. So period integral is a pairing between some twisted drum complex, drum homology, and untwisted singular cohomology.
Why twisted?
Twisted is, for example, hypergeometric function is integral x alpha 1 minus x beta 1 minus tx minus c dz like this, but and this is cohomology for of curve. This is a pairing of two things, and this, for example, omega is contained in H1 of so something like M04, but this is so if T is variable, then this is relative cohomology. So if T is equal to 1, then it is related to something, and the quotient here is twisted by x to the alpha 1 minus x to beta minus 1 and 1 minus tx minus c, something like this. And therefore the quotient is already local system. We must twisted drum homology means cohomology with quotient in local system. So we must we must define these things associated to associator. This is first thing. Second thing is we must show that zeta phi. I already defined zeta phi associated to associator of 2a, 3, 2b, and take y 2a plus 1, x 2b, something like this is equal to. First, we must define periodic integral associated to associator, and if we define periodic integral, we can define from this we can define hypergeometric function. So phi hypergeometric function, say f 3, 2, phi, and so on. Then, if we define this phi hypergeometric function, this the next step is to show that this is something sy. Phi here we must show this equality.
You don't have
And also,
y minus 1 in the fifth argument? Or
1 plus 1, y minus 1.
or 1 minus y? Or
1 minus 1. Yeah.
Plus 1 of I.
And also sum of right hand side, y to 2a plus 1, and x to 2b is equal to linear combination of psi function. So second, first we define a period. Therefore, by using this period, we can define phi hypergeometric function. And the second, this phi hypergeometric function is actually a generating function for the quotient of associator. The third is this is equal to this 1 is equal to 2.
In 2, there's no mention of phi.
Hmm?
There's no mention of your associated phi.
3, 2.
In the second equation, you need to put some phi in the notation. The psi function has to...
Phi, yes, phi function. Right hand side is also phi. Now we give first step is to redefine period integral. As I said that phi gives an isomorphism between u bet m0 n c to u drum m0 n. We use this isomorphism. First, we consider category C, category T. This is defined by object is defined by object consists of 2 vector space and 1 isomorphism. 2 vector space and 1 isomorphism between this B tensor C and B drum tensor C. This is abelian category and abelian tensor category, and also this is Tandakian category. And since phi is isomorphism of functorial isomorphism of Hopf algebroid, therefore phi m0n, we extend factorial isomorphism.
So C is an isomorphism, I expect?
This is isomorphism.
C, I mean in your definition of T.
Hmm?
In your definition of your category T.
This is isomorphism. So this defines a Hopf algebroid object. Hopf algebroid object in T. Therefore, using this, so it is therefore it is written U phi m0n. This is Hopf algebroid object. So this is strictly speaking, this is system of object in T indexed by 2 points, and multiplications are in this category. So morphism is, of course, morphism between wedge part and morphism between drum part, and isomorphism should be compatible. This is morphism, and this becomes so Hopf algebroid object in T. therefore, so suppose then we can define a notion of module, U module, U5 module. We can define notion of U5 module M in as in algebroid module over algebroid. So this is indexed by one object. So U5 module means U phi something AB. U phi is this is called U phi. Tensor M. So maybe E to M A. This morphism is morphism in this is compatible with comparison map. So in this way we can define a module U5 module, notion of U5 module.
Finite dimensional.
Yes, finite. We sometimes consider finite dimensional, and also sometimes consider finite rank over like these things. For example, this is if you consider this, then these things, then quotient should be this module over this formal power series ring, commutative formal power series ring.
So when you mean module, do you mean for each? You mean a Hopf algebroid co-module?
What's
the sense of the word?
I said maybe it's better. This has coprod. This is U bet is as I defined. So Hopf. Maybe it is how to say this is dual Hopf algebra. Maybe this is correct word because so antipodal is reverse how to say not algebraic. This is anti-isomorphism. So maybe it is called dual Hopf algebra.
So what's the definition of M, a module?
Definition of M is system of object in C which has this action and which satisfies associativity relation. This is the definition of U5 module.
So C vector space, this tensor over C. At least I should know. So what do you
this is
at least vector space, right?
MB. MB is consistent. MB is an object in C, so MB. This is object in B, so bet MB, drum, and comparison. And this is morphism. Morphism means everything is compatible with comparison morphism. Then we can define a cohomology of M, cohomology of M0n with the quotient in M. So definition, phi cohomology of, so this is a mixture of drum cohomology and bet cohomology, and comparison is given by us, obtained by associator. This is defined by the cohomology of the following complex. the complex is like this. Home A N U U phi. U phi is U phi M N M0 N and U phi M home U phi tensor U phi M and so on. And this map is given by U phi tensor U phi to U phi tensor U phi tensor U phi. This goes to X tensor Y goes to XY minus Y X times epsilon Y. And epsilon is augmentation. So to define this, we first choose a base point here, base point M0N, infinitesimal point of M0N. Then epsilon is U phi XX to Q. This is augmentation. So dual to the embedding to the identity elements. This is augmentation map is denoted by epsilon. Then this map, and also, so for example, this X tensor Y tensor Z goes to XY tensor Z minus X tensor YZ plus X tensor Y epsilon T, and so on. Then fact is that this is this morphism. This morphism is in this category T, and therefore this is complex in the category T. And this homomorphism is actually this is inner homomorphism. So this is in the category T. Both are in category T, and this is also in category of T. This is closed under home. This is Tannakian category, and this is closed under taking home. Therefore, this is in category T. And taking the cohomology, then this is object in category T. Therefore, we have isomorphism between drum part and wedge part. Therefore, we have an isomorphism between drum part of M0 and M drum. I wrote upper drum. C and isomorphism between upper wedge M0 and maybe vice versa. M0 MB tensor C. So we have this isomorphism. On the other hand, for example, HBI M0N M B is isomorphic to usual twisted cohomology. So usual singular cohomology. And drum is usual drum cohomology. But the isomorphism between this is not classical comparison map, but this comparison map comes from associator. Comes from associator. But for example, we consider if you so we can define such.
Don't you need an assumption on M for the comparison to come from an associator? M has to be in the subcategory of T generated by U phi. Doesn't M have to be in the subcategory of T generated by your Hopf algebroid?
Not necessarily.
Otherwise, how can you compute the pairing?
Yes. Coming from associator and comparison map of M. Yeah, comparison map of M. So if M comes from, so if M comes from the data of comparison map of U phi, then this coefficient can be written in terms of the coefficient of associators. For example, we have such integral. This integral becomes essentially beta function. And for example, we, to define this in this setting, we consider the following local system. So using this, we can define phi integral of this. For example, this is U phi M04 equals U phi M04, and this is so drum part. For example, drum part is isomorphic to this one, and we consider the abelianization of this. Then we get this commutative formal power series rings. And we said E0 is equal to alpha, and E1 is, we said E0 is equal to alpha, and E beta E1 is equal to beta, then this becomes formal power series ring of alpha and beta. And so we to define this, we set M to be U phi of M0 M04. Then this becomes phi U phi module. Strictly speaking, we must choose something and certain point P for P, where P is in infinitesimal point, because module is indexed by one index. So if we fix one reference point, then this becomes a U phi module. And if we consider cohomology with M04 H1 drum, then we have this element x dx omega. This is element in drum cohomology of M04 with coefficient in M drum, and H batch 1 we have M04 and batch, then we have x to the alpha 1 minus x to the beta lying on 0, 1. The section of x1 to the alpha times x minus 1 minus x to the beta, and it is the branch of this on 0, 1 is given by a real number. So this is specified branch on 0, 1. Then, so
what is W? You've written H1 Duran.
Alpha. Then so first we using this we can, for example, we can define beta function. We can define beta function, but this is truly speaking, this is not beta function. This is a little bit shifted. So I write beta star of alpha and beta. So we can define phi version of beta alpha beta is using the pairing x dx alpha and x 1 minus x to beta x 0, 1. The pairing is defined by there is also duality, and also we have duality. And the pairing depends on this phi. This isomorphism depends on phi. So we can define such things. So and also we can define many things for hypergeometric function. But this is a function. So to define hypergeometric function, this is M05 xt to x t x and M04. We consider map from M05 to M04 by forgetting the second variable. We get such map, and hypergeometric function is defined by R1 f lower star m. M is defined in the same manner, and then this becomes mu phi M04 module. So hypergeometric function is defined as a U M04 module.
This is a F21 hypergeometric function.
FQ1.
F21? For F32, you want to go from M06 to M05, don't you?
For 5 to 4.
So which hypergeometric function is this?
Geometric.
Which hypergeometric function is R1 F lower star M?
This is
The Gauss.
Hmm?
The Gauss hypergeometric.
yes. So sheaf is x to the x to alpha minus 1 minus x c minus alpha minus 1 and 1 minus. So integration is t. So integration is t.
But
So
it's 2F1.
Sorry. So minus beta. So this define sheaf on this. On the higher direct first higher direct image of this sheaf is this become this module, and this module corresponds to. So this module is the data of this module is Gassman connection on M04 plus local system M04 plus some funny isomorphism induced by associator phi. So we can define this phi relative phi cohomology also. So this is the first part. So we define hypergeometric function, and also we define coefficient. There is coefficient of associator. And the next question is: actually, is it true that generating function for coefficient of associator is equal to hypergeometric function? The second part is this sigma of theta phi to x to not something and y to something is equal to hypergeometric function, or differential of hypergeometric function. So this is the second part. This second part is very difficult to explain. So I want to skip, but the main idea is like this. Main idea is like this way. If you have, say, R1 F lower star M, then this is we know that this is phi M04 module. What is the meaning of this phi M04 module? This is so the meaning is R1 F lower star M drum part has an action of E0 and E1. And as I said, this is the data of this module is equivalent to give Gassman connection. And the Gassman connection is given by this space B to B tensor B D D Z plus, and this action of E0 E1 gives map. Usually we use duality, so the dual action. So M goes to E0 minus E0 ZDG plus E1 Z minus 1 ZG times M. Then this is the last one connection. Now it is we can for hypergeometric function this is we can easily compute for hypergeometric function. We know this. What is this? So E0 is equal to something. If you use alpha, beta, gamma like this, then E0 becomes something like 2 by 2 matrix. So because hypergeometric function is rank 2 differential equation, so this is written by 0a, 0 minus like this. A and B and C is alpha, beta, gamma. Here like this. And alpha, gamma, and E1 is equal to something like this. So it is very classical computation for hypergeometric functions. Minus 0, 0, minus beta, gamma minus alpha minus beta, like this. Then this coefficient is every coefficient in C alpha, beta, gamma, and therefore E0, E1 is nilpotent, topologically nilpotent. E0, E1 is topologically nilpotent action. And using this, since this comparison map is given by comparison map is compatible with this action. So this is this module has this action. This is action. Therefore, what is the meaning that action is compatible with this M0 U phi M04? That means if you consider this, then something like given associator evaluated by E0, E1, then this becomes an element in 2 by 2. So E0 and E1 is 2 by 2 matrix. Therefore, the composite has multiplication is also 2 by 2 matrix, and this is contained M 2 by 2 matrix with coefficient in C alpha, beta, gamma. Okay, and we evaluate some two vectors. Then this becomes element in C alpha, beta, C alpha, beta, gamma.
There is a question.
Yes.
To end the general philosophy, you associated before in the 4-point case, M04, that alpha corresponds to E0 and beta corresponds to E1.
Yeah.
So here we have a one-to-one correspondence between the two-letter alphabet.
Yes, but this is not a one-to-one correspondence. So there is also, I think M05 contains, if you choose parameter freely, then there is 5 freedom of taking parameters.
Okay. Now in the
but we only use 3, so we do not use everything.
But how is it now with M05?
Yeah.
Naively, I expect 5 parameters, 5 defining exponents for my hypergeometric function.
Yeah.
And is it fair to say that your matrix construction, that this bypasses the gap between 5 parameters and 2 letters in the alphabet, E0, E1?
If you, I don't know. Maybe if you how to say, use 5 parameters very freely, then this becomes a hypergeometric function times very easy function. I think it becomes.
But how does it relate to the counting? For M05, I have 5 characters.
5 parameter is so this is so if you consider C2, then 1, 2, 3, 4, 5, and we can put exponent alpha 1, alpha 2. So 5 exponent is free, can move freely. So 5 parameter, but we only use, this is essentially integration over M05. This hypergeometric function is, yes. I want, 5 parameters. So this is integrate x to something, 1 minus 2x to something, 1 minus 2 dx to something, dx dt. So, so 2 variables here. So this is essentially a configuration in M05. This gives x is the singular locus is given by a configuration.
And what's the reason you are not writing t and 1 minus t? I would have naively expected a t to some extent.
Yes, maybe it's better to rewrite t inverse. So essentially, this is equal to t minus x.
Oh yeah, I fully agree. I fully agree. Yeah.
So maybe t inverse is correct. So familiar parameter for integration. So this is the way of showing. Okay. Okay. I erased, but this is how I get the relation, second relation. And third relation is third part is so two hypergeometric function is equal to another hypergeometric function. So psi is in some sense. This is also this is d log gamma. So gamma is a part of hypergeometric function. This is not hypergeometric function, but a part of hypergeometric function. Therefore, this is expressed by using period, this phi period. Therefore, so left-hand side and right-hand side are hypergeometric functions. And the last part is these two hypergeometric functions actually coincide. That is the last part. So usually, to show the equality of period is induced by many equalities are induced by algebraic correspondence. But in our setting, not all algebraic correspondence are allowed. The algebraic correspondence we can use is induced by so how to say successive so composite of so this M0n to M0m projection, natural projection, and also M0n to M0n infinitesimal inclusion. These two type of morphism is allowed, and so the last thing I must show is that the correspondence inducing this equality actually comes from this restricted correspondence. The fact is,
when you write, did you write infinitesimal inclusion, or is the second line infinitesimal inclusion? Is the second line, last line?
Second line.
So the
down,
lowest
down.
line, we cannot read. Inco?
Infinitesimal inclusion.
Okay.
This is, if you want some algebraic correspondences, how do you use?
Not arbitrary. Arbitrary correspondence does not induce morphism of phycohomology. So the
But I mean,
morphism
how
should.
do I think of this infinitesimal inclusion as a correspondence? Correspondence.
Infinitesimal inclusion. So
It's not algebraic. So
this is in classical sense. It is not morphism of algebraic varieties. So truly speaking, this is not algebraic correspondence. But we also use this infinitesimal inclusion to show this.
okay.
Identity. So this is not algebraic correspondence. Sorry, this is not.
This is not okay.
Not classically algebraic correspondence, but we can use this infinitesimal inclusion.
Okay.
So this is the outline of the proof. So this is not. As I explained, this is I proved the Brown-Zagier relation for associators, but this method is applicable to many situations and many relation can be proved for associators using this method.
Oh, thank you very much. Are there any open questions?
Many relation means, for example.
For example, easily, for example, like this is very trivial, but x, y plus g. For example, this is using algebraic correspondence in this sense, x, y. Like this, for example, like this relation.
So once we know gamma decomposition, then this is a easy consequence.
But the logical way is vice versa. First we define beta module. After that we show this equality. So this is Planck cycle condition for beta function. Therefore, from this we can conclude that this can be there exists gamma, unique gamma, such that this holds. So first we define beta function, and this beta function satisfies this relation. Therefore, its beta function can be written like this way. Then this is unique, so we can define gamma function, and we can define psi function like this. But this is one for example.
And presumably double shuffle equations? Presumably you can do double shuffle equations.
Yes, double shuffle equation is not proved like this way, but
on an open if you do the same game on some open subset of M0n, removing all diagonals, I imagine it's...
For to prove this regularized harmonic shuffle relation, we also do in this framework, and but to show this regularized harmonic shuffle relation, we must consider it is better to consider a nearby cycle functor and a nearby cycle functor.
I'm saying something much more simple. You can prove that the double shuffle stuff equation has some identity on integrals, but not on moduli space, smaller space.
Yes,
very
identity on integral, in some sense integral, but a higher direct image. So convolution product is equal to some, so there's
a very simple proof of the Stoffel equation, just integrals, a change of variables of integrals, but geometrically it lives on an open subset of M0n. And if you write phi for every integral...
for harmonic configuration, you mean?
Yes.
Yes.
Phi, but it's just on a different space, slightly different space.
Yes. But that is one way. But yes, that is one way. But if you treat with regularized one, we must
after regularization.
This to get regularized one. We must this and plus convolution. So how to say? Green gave a very funny category, phi, f perverse sheaf, and with a convolution product at one convolution, and perverse sheaf which is smooth outside of 0, 1, infinity, and fiber functor is nearby cycle functor at f, then this becomes actually fiber functor reserving this convolution because of this Fourier transform formula. This is so convolution corresponds to tensor product in this fiber functor. Then this if you consider this one, then you get double shuffle group, and how to say? So there is universal object here. So this is equivalent to certain category of A module. A module A is generated by y1, y2, yi is equal to e0 to I minus 1, e1. Then this is considered as a subring of e0, e1. And but the ring structure. So this is infinitely generated ring, subring of this two generated subrings, and this module is interpreted as a category. This category modulated up to some equivalence. Then this has a product here. Therefore, A has a coproduct, and this coproduct.
The coproduct on the y's is not a sub. It's not a sub-Hopf algebra.
Subalgebra. Hopf algebra structure is different from algebra. Hopf algebra structure is given by this convolution product. Then this y n of this is equal to sigma y. This a little bit different Hopf algebra. So using this game can be also applied to this phi associator setting. And if you use associator setting, then we can show that any associator satisfies double shuffleization. Okay. Maybe you will also prove and in much more how to say direct way.
Thank you. Last time.